Okay, let me maximize this. Turn on the light. Yeah, please do. Thank you, Cameron. Thanks. All right, so anyways, did everyone get the worksheet? The gas laws worksheet? So flip to the back. We'll use the back for notes. And what I want to talk to you guys about today is essentially in 10.5 in your book. And section 10.5 in your book, let me expand this, is called Further Applications of the Ideal Gas Equation. And I need you guys to put your algebra hats on. All right, so here's one application that we're going to talk about today. We're going to talk about how you can use the ideal gas equation to relate the density of a gas to its molar mass. So we're going to use the ideal gas to calculate molar mass. And now look at what I'm going to do. Molar mass has this symbol. It looks kind of like a big capital M. And I try to make it kind of cursive-y there. Here, I'm going to make it a little bit like that. To help distinguish it from the symbol for molarity. All right? This is where it's going to get a little bit confusing because when I type up labs, my favorite font is Arial. So when I try to type that on a lab, it looks like a capital M, right? And unfortunately, that's the same symbol that we use for molarity. So it's going to be really critical that when you're looking at a piece like a word problem, that you realize whether you're dealing with a gas or you're dealing with a solution. Because if you're dealing with a gas, that big capital M represents molar mass of the gas. If you're dealing with a solution, that big capital M represents the concentration. Is there someone at the door? I thought I heard something. All right, anyways, so we're going to use the ideal gas law to calculate the molar mass. I'm going to put that in parentheses so that you know what that symbol means, from the density of the gas. Okay? All right, so we learned at the beginning of the school year that density is one of these properties that can help you identify a material, right? So density is a property that can help you identify a material. Why can't it help you identify a material? What's that, Adit? Right, because it's independent on the amount of the sample. So it's an intrinsic, or actually it's an intensive physical property. We call them intensive. Now, not only is it independent on the amount of the sample, but it's also unique for different substances. All right, so if you were to come to me with a liquid, a clear, odorless, tasteless liquid with a density of 1 gram per milliliter, I would tell you, oh, you just gave me a bunch of water. All right? Because the density for water is 1 gram per milliliter. Now, we can use density to figure out like the identity of a gas too. Okay, and so we would use it this way. We'd use density, right, that we measure in the lab, right? It's something we can measure. We would take that information and calculate the molar mass of whatever substance we were given, and based on that molar mass, we could start to identify what that what that substance is, what that gas is. So say for instance, for example, I measure the density of a colorless gas. Let's make this a flammable gas while we're at it. And I use that density to calculate its molar mass. And that molar mass calculates out to 2 grams per mole. Right? What is the gas? There's only one possibility. Hydrogen, right? Can it be anything besides hydrogen? Can it? No. Because the next lightest gas on the periodic table is helium. And how heavy is helium? 4. That's too big. Okay? So what I'm saying is I measure the density of this gas. It's an unknown. Someone just gives it to me in a vial. It happens. I can test that I can see it's colorless. I can test that it's flammable. From that density, I can calculate its molar mass. From my calculations, it tells me it's 2 grams per mole. I know what it is. I know it's hydrogen. Okay? Here's another example. Say I get another sample of a gas, also colorless and flammable. It yields a density that allows you to calculate a molar mass of 32 grams per mole. What is the gas? Is sulfur a gas? Oh, it's not. Okay. Sulfur's not a gas. But oxygen, if you think about the formula for oxygen, what's the formula for oxygen? If you calculate the molar mass for O2, 2 times 16 is close to 32. All right? So it could be oxygen. Could it be something else? Maybe. What if it was an organic hydrocarbon? Could it be an organic hydrocarbon? How many carbons with that hydrocarbon could it have max? How much does carbon weigh? 12. So let's think about that. Could this hydrocarbon have 2 carbons in it? Could it have 3 carbons? So it could have 2 carbons, but it can't have 3 carbons because 3 times 12 is 36, and that's too big, right? So could it be, let's see, if you got 2 carbons, what else does it have to have around it? Hydrogen. So then what would be the molar mass for this? 24 plus 6. 24 plus 6 is 30. If you account for any experimental errors, is that in the ballpark? Could that gas be, what is this called? What's that called, guys? Ethane. Could it be ethane? Sure, maybe. Measuring the density for something heavier might not exactly pinpoint the identity of the gas, but it would help me narrow down the field. I know it's not hydrogen. I know it's not helium. I know it's not neon. I know it's not argon. Right? There are some things I know it's not, but I could narrow down the field to a couple of substances, and then I could do further experiments to definitively pinpoint, is it O2 or is it methane? Okay, what's a simple experiment that I could do? If I had a sample and I didn't know if it was oxygen or ethane based on molar mass, what could I do to prove one or the other? Could I set this on fire? What would I make if I set this on fire? Carbon dioxide and water. So if I could make water and it had that molar mass, it's probably ethane. Would I make water if I set that on fire? No. Okay? So you could do some follow-up experiments to definitively say, okay, it's ethane. All right? Okay, so how do we take density and calculate molar mass using the ideal gas equation? Okay, so here's the deal. We're going to have to take 3 equations, 3 definitions, and make one master equation in order to do that. Okay, and so now we're going to spend about 5 or 6 minutes deriving this. The only reason why I'm doing this is not because I expect you to be able to do this. At the end of the day, you're just going to memorize the final equation. But in reality, when you're in the lab, one of the things that I want you to kind of wrap your mind around is that scientists do this all the time. Maybe there's one equation that allows them to figure out one part, some clue about a compound, and there's another equation that allows you to derive a second clue about a compound. You can take those equations and put them together to try to derive a third clue about a compound. Okay? And all it requires is substituting one equation into the other, provided that they have common variables. Okay? On that AP exam, those free responses are all about connecting dots. All right? They're going to bring information from different units into one question, and you have to be able to bridge what you learn in this unit to what you learn in that unit to figure out a third thing about that substance. And this is very common practice in science. Okay? Things are not black and white in boxes. You have to be able to connect dots between subjects. So that's kind of what we're doing here. All right, so let's talk about this. So we want to be able to relate density and molar mass. That's kind of what we need to do. All right, so let's talk real quick. So what is the formula for density? So density is mass. What symbol should we use for that? Lowercase m, okay? Over volume. What symbol should we use for that? I'm going to use a capital V. It is. It's like a heart for volume. All right, what about molar mass? What's the definition of molar mass? When I calculate it off the periodic table, what are the units for molar mass? No, it's not atoms per mole. If I calculate the molar mass of oxygen being 32, is 32 right? So what's the unit on it? Grams per mole, right? Okay, so molar mass is grams per mole. Do I use the symbol G for that? What symbol do I use for that numerator to represent that? What's the symbol for mass? Isn't it a lowercase m? Yeah? Isn't it little m over, what's the symbol for mole? What is it? N? Okay, all right. Okay. They have a common variable. All right. When you have common variables and I want to combine these two to relate this to that, how do I do that? you can substitute one equation into the other. But it would be a little bit easier if we solved both of them for m, right? And set them equal to one another. How do you solve this for m? Little m. Little m is density times volume. What's little m over here? What is it over there? Molar mass times number of moles. Now that you've set both of them equal to m, now we can say, we combine them, d times v is equal to molar mass times n. All right? All right, well, here's the deal. Can I measure density of a gas in the lab? Easily and directly. Yeah, you take a gas, you put it in a balloon, you weigh it, and you figure out the volume of the balloon. Can you do that directly? So I can directly measure this. Can you measure the volume of a gas directly? Yeah, you can do that too. So you can directly measure both density and volume. Can you measure the number of moles directly? Can I sit there and I count 1 atom, 2 atoms, 3 atoms, 4 atoms? I can't do that directly. But I can measure it. Unfortunately, I have to measure it indirectly. So D, V, and N are things that I'm going to measure in the lab, and that's going to allow me to calculate molar mass. All right, well, how do I measure moles of a gas indirectly? Well, what equation did we use the other day that had N as a variable? PV equals nRT, the ideal gas law. All right, so let's do something very similar. So you know how we brought and put these two equations together? Let's insert a third equation. PV equals nRT. All right. Solve for N. What's N? N is equal to PV over RT. Can I measure the pressure of a gas pretty easily? Yep, I can measure that. Can I measure it directly? Sure. I've got this little pressure sensor that connects to my computer that lets me do it. It's a little barometer, gas pressure sensor. I'm sure if you had honors chem, you played with them before when we did Boyle's Law labs. Can you measure the volume of a gas? Did we say that you could do that directly already? Yeah, this you can also measure directly. Can you measure the temperature of a gas pretty easily? Sure. So these are things that you measure directly. You use those to calculate N. Once you have N, you substitute it in here. All right? Okay, so let's take this equation here, the dV equals capital M over N, and substitute in PV over RT, and see what we get. All right, as a final step. So let me rip this paper off and show you. So dV equals capital MN, and N equals PV over RT. So what I'm going to do in this final step to get this final equation, this is the one that I really want you to memorize, is I'm going to take PV over RT and I'm going to substitute it in for N right there. All right? So what do you get? You get dV is equal to M times PV over RT. All right? Okay, now isolate M for me, capital M. What's capital M? Capital M is dV RT over PV. So all that Adit did is multiply both sides by RT over PV, right? Okay. All right, take a look at what happens here. Is there a variable that cancels out? Which one? So this final equation, which is the one that you have to memorize, which is a combination of of all three of these that we just discussed is m equals dRt over P. And this is the one that you memorize. This is the one that we're going to use in sample problems. Okay? And again, I don't expect you, bless you, to do this derivation, but you should be aware, oftentimes, you can take equations and shove them together like this and use them to extrapolate information about a material that goes above and beyond. Okay? All right, so let's take a look at how you use this. So on page 408 of your book, actually 407 and 408, there's a couple problems that I want to do. So page 407, sample exercise 10.7 asks the following. It asks, what is the density of carbon tetrachloride? So they're telling me I've got CCl4, that's the formula. They want to know the density. Page 407, it's up on the screen. If the pressure of this gas vapor is 714 torr and the temperature is 125 degrees Celsius. All right, so they're asking us to do things a little bit backward. They want density, not molar mass. All right, so here's my master equation that I'm going to play with. I've told you before, I really like to go ahead and figure out the variable that they want and isolate the equation for that variable and then substitute. So how would you get D alone? If I had to rearrange this solving for D, what would this equation look like? D is equal to MP over RT. All right. Do I know the molar mass of carbon tetrachloride, or can I easily calculate it? Can I calculate it? I know the formula. What do I look at? You take the formula weight off the periodic table, right? So the formula weight off the periodic table is 12 plus 4 times the mass of chlorine, which happens to be 35.5. If you sum that up, the molar mass is 154 grams per mole. Okay? All right, now, I know R. R is pretty easy. It's 0.0821 LATM over mole times Kelvin. All right? So I'm going to go ahead and substitute it into my formula. And you've noticed that for P, I just put some parentheses and I've left them blank. And for T, I've just put up some parentheses and I've left them blank. And the reason why I've done that is because I want you to realize that the information that they gave me in the question is not in the correct unit. How do I know that? Whatever unit they give you has to cancel out with what? The units for R. I don't care so much that you memorize that R is 0.0821. What I really care about is you know that unit. That unit dictates what these units should be. All right? How should pressure be described in atmospheres? So how do we change that to atmospheres? You divide it by 760. I'm going to go ahead and just write 714 over 760 over there in the parentheses. Because I'm technically not going to pull out my calculator until the last minute, and I'm only going to do one single step in my calculator and round once at the end. All right, what about the temperature? According to that unit right there for R, what does temperature have to be in? Kelvin. And how do I change that to Kelvin? It's 125 plus 273. So once I've got everything substituted in and I know how I'm going to change these units, then I enter it into my calculator all at once. So I do 154 times 714 over 760. I'm going to take that answer divided by 0.0821. Okay? And I'm going to take that answer and divide it by 125 plus 273. Okay? How many sig figs should I round my answer to? Well, look at all your givens. All your givens were to 3 sig figs, right? So, there you go. What's my answer? Okay. I'm going to be a jerk. I'm going to ask you for units. What units do you put on this? So now take a look at your work here. Let's cross out what cancels. Oh, oops. Let's take a look. ATM cancels out with ATM, right? That's a K down there. Kelvin cancels out with Kelvin, right? Mole cancels out with mole. What's left? Grams per liter. When you describe the density of gases, it's typically in grams per liter. Even though in the past, we did grams per milliliter. All right? So remember, the density of a gas is much less than that of solid, so we're using a different scale here. Okay? All right, so that's my answer. Was that so tough? No, not really. Okay, let's go to the next page, page 408. And I'm not going to do sample exercise 10.8, but I'm going to urge you to look at this in your free time. This is what your lab is going to look like. Those are the kinds of calculations that you're going to have to do in the lab next week. Okay? So if you've got a couple moments, just take a look and see, because they describe the entire lab procedure for you, or something very similar to what we'll be doing. Okay? I'm going to do the practice exercise on the bottom of page 408, just so that you can see how to do the math with this formula. So it asks me to calculate the average molar mass of dry air. So they want M, capital M, if the density is 1.17 grams per liter, the temperature is 21 degrees Celsius, the pressure is 740.0 torr. All right? Okay, let's start with the equation that relates density and molar mass. Well, what is that equation? M equals dRT over P. Just memorize this. This particular equation is not on the reference sheet for the AP exam, but it makes life so much easier if you use it. Okay? All right. Do you want to talk to me about these units? Is that an appropriate unit for the density of a gas? Yeah? Is that the appropriate unit for temperature? No, so we're going to have to add 273 to get it to Kelvin. Is that the appropriate unit for pressure for this kind of an equation? No, what should it really be in? Atmospheres. So what are you going to do to get it to atmospheres? Divided by 760. So let's substitute in here. 1.17 gram per liter times 0.0821 times the temperature of 21 plus 273 over a pressure of 740.0 over 760. So I go ahead and do the conversions all in my calculator at the same time that I'm substituting. And because I'm a friend of parentheses, it's easy enough for me to do that. Just type it all in one sentence, hit enter. I get 29. And you know I don't like to just see numbers that are naked without a unit. What is the unit for molar mass? If you have a hard time figuring it out, cancel out the units that are in the problem and see what's left behind. All right? But I'm going to tell you it's grams per mole. All right? Okay, any questions there? This is the majority of your homework out of the book. You've got 5 problems tonight to do on page 428. The bulk of it is this kind of stuff. You're just plugging into this one. All right? Questions? No? All right, let's go to the gas laws worksheet, that part 4. So flip to the front side, because you were taking notes on the back of that, right? This is easy stuff. Easy stuff. All right. There may be a question or two in the book problems there are of this variety. Let's start with this top part. The top part is all about a Avogadro's hypothesis, which we kind of talked about yesterday in going over the homework. Let's read this together. So part 4 is all about gas stoichiometry. All right, so you know how you had a stoich quiz earlier in the week? And it was all on ideal stoich and limiting reactant? Maybe next week you'll have a little quiz on gas stoich and solution stoich, just to get you ready for the next test. Whatever that may be. I got to figure it out. All right? So gas stoich. So the other day we were talking about how when you have a balanced chemical equation, so for instance here you have one, 2CO plus O2 yields 2CO2. When we were doing stoichiometry, we learned that those coefficients meant moles, right? So the way that you read this is that you have 2 moles of carbon monoxide reacting with 1 mole of oxygen. You end up making 2 moles of carbon dioxide, okay? With gases, it could mean something else, all right? And this is really critical. So long as the pressure and temperature are held constant, and so long as that is true, those coefficients can also mean liters or volumes, all right? So that if this was constant, right, so that those are conditions that don't change throughout the reaction. What I can also say is that 2 liters of carbon monoxide react with 1 liter of oxygen, and you end up making 2 liters of carbon dioxide. All right, so you can call them liters as well, so long as pressure and temperature remain constant. Okay, and so that makes life really easy for this sample problem that's down here. Let's look at what they're asking in this question. In this question, they're telling you that carbon monoxide reacts with oxygen to produce carbon dioxide. If 1 liter of carbon monoxide reacts with oxygen at STP, and by the way, what does STP stand for? What does that mean? That's 0 degrees Celsius in 1 atmosphere? How many liters of oxygen are required to react? Okay, well, if you didn't know this information, you could do that problem. It'd be very long and tedious, okay? Because what it would require for you to do is to take that volume, that temperature, that pressure, use the ideal gas law to figure out how many moles of carbon monoxide that is, and then take the moles of carbon monoxide, multiply it by the mole ratio to figure out how many moles of oxygen you need, and then take the moles of oxygen, that temperature, that pressure, stick them back into the ideal gas law to get the volume. So basically it'd be doing ideal gas law twice with a fence post in the middle. That takes up a lot of paper. Okay? When I can do it just within 1 step. All right? Here's how it's done. Provided temperature and pressure stay the same, all I would really need to do is do a fence post that has the given up there in the upper left-hand corner, all right? And take a look at the conversion factor over here. All right, so the conversion factor, instead of doing a mole ratio, I do a volume ratio. So you would put liters of carbon monoxide in the denominator so that those units cancel out, liters of oxygen in the numerator, and the numbers here are essentially your coefficients. All right, so it's like a mole ratio, but instead of using moles, you use liters. Look at that. So then it's 1 times 1/2. What's the answer? So the answer, you can calculate very quickly in your head without even pulling out your calculator, right? Because 1 times 1/2 is 1/2, right? 0.5. And I did it with one cheesy little fence post in about 10 seconds flat. How long do you think it would have taken you to do ideal gas law twice with a fence post in the middle? About 7 or 8 minutes. You want to avoid that, okay? I will tell you that some AP Chem teachers don't teach their students this at all because they expect that their students will still be able to do it the other way. I'd rather you have this little trick in your back pocket to save time because, again, that free response, what makes it challenging is that half of you guys, when you go take that test, you're nervous. right? And you're having a tough time looking for information in your memory banks. And the last thing that I need you to do is to get overwhelmed over a calculation that could potentially take upwards of 15 minutes when you're only given 10, when in fact you could do it knowing this simple little trick in half a second flat and move on with your life. Okay? So be aware that you can apply this trick, provided what? Pressure and temperature is constant. It doesn't have to be standard temperature and pressure. Just pressure and temperature has to be kept constant. Okay? You have to be told that in the question. All right. Let's take a look at question number 1. I want to do A for you, and then I want you to do B and C on your own and see what you come up with. All right, so it says acetylene gas undergoes combustion to produce carbon dioxide and water vapor. All right, so first things first. It's a stoic problem. What do I need? Balanced chemical equation. Well, I didn't give it to you. But you're smart enough. You've had 2 quizzes on reactions now. You should be able to give me that equation pretty easily, right? So acetylene, C2H2. I'm combusting it. What do I need? What am I going to make? Is that equation useful for me for stoichiometry purposes right now? Is there something missing? I have to balance it. Okay, so let's balance it. You would have to put a 2 in front of the carbon dioxide to balance out the carbons. Hydrogens are balanced out. But take a look now. How many oxygens are there on the right-hand side? No. Count again. How many oxygens in the carbon dioxide? 4. Plus 1 more is 5. How do I get 5 out of that? You multiply by 5 halves, because 5 halves times 2 is 5. Am I allowed to leave fractions like this? No, so what would I do? I would multiply the entire thing by 2, so my final equation would be 2C2H2 plus 5O2 yields 4CO2 plus 2H2O. All right, take a look at the question that they ask. How many liters of acetylene are required to produce 75 liters of carbon dioxide? All right, so I'm going to do my fence post. In the upper left-hand corner, I'm going to put in my given. I've got 75 liters of carbon dioxide. On the far right, I'm going to write the unit that they want me to go to, liters of C2H2. Okay, here's my conversion factor. In the denominator, I'm going to put liters of carbon dioxide. In the numerator, I'm going to put liters of acetylene. All right, how does this relate to that? I look at the coefficients in the balanced chemical equation. You need 2 liters of acetylene for every 4 liters of CO2. All right? Don't even grab your calculators. If I see anyone grabbing their calculators, I'm going to beat them. What's 2 divided by 4? Half. What's half of 75? Come on, kids, quick. What's half of 75? Okay. Half of 75. Really? 37 and a half, right? I did. I had to assume that because I wrote the worksheet, and that's the intention of what I wanted you to get out of this. But on a real test, you would have to be told that. It's just that I need to go back and add that to this worksheet. I failed to write it down when I was writing it. Okay. Okay, take a minute, do B and C. So let's see what you come up with. Okay guys, when you're done, you can check. My answers are up there. Did you get that? Any issues? It's pretty straightforward stuff. You may have noticed that this is an ideal stoichiometry question. Could I have done this in the context of a limiting reactant problem? Sure, I could have. Was I feeling mean enough to do that to you? No. Could I one day? Maybe. But we're going into a 3-day weekend, so I'm not feeling so bad. All right, so let's look at the next part. All right. How else can we do stoichiometry with information about gases? All right, so let me scooch this up so you can see. And let me highlight something here. All right, so now when pressure and temperature aren't standard, or when one is asked for moles or grams of a product given volumes of a reactant, then you have to take a slightly different approach. And that approach requires that you use basically a fence post in combination with the ideal gas law. So sometimes you have to use the ideal gas law first and then the fence post. Sometimes you got to go in the other direction. You have to do the fence post first and then the ideal gas law, depending on what they give you and what they ask for. So usually the rule is this. So if they give you moles, you have to do the fence post first and then use the ideal gas law. If they ask for moles, it's the opposite. You have to use the in the opposite order. Well, let's take a look at what they do here. They say assume that 5 liters of hydrogen gas at STP reacts with copper 2 oxide according to the following balanced equation. They give it to you. Now, one of the things I should warn you is that, and I'm sure you guys saw this after your first quiz, especially those of you guys who had the yellow quiz. Just because there's an equation typed up for you, don't assume it was balanced. Okay? And to be perfectly honest, I don't trust my own shadow. I always double check that the equations are balanced. Okay? Is this one in particular balanced? Is copper equal on both sides? Is oxygen equal on both sides? Is hydrogen equal on both sides? Okay, so now I will move on from this point. It asks how many grams of copper are produced. All right, so what I like to do, again, anytime I got any of these word problems, is I like to write the balanced equation on my paper, and I like to go back at that word problem and look at the numbers that they've given me, so and write it underneath the substance that it's referring to. All right, so they're telling me that I have 5.60 liters of hydrogen, and that hydrogen happens to be at STP. So what does that mean? It's at a temperature of 0 degrees Celsius and at a pressure of 1 atmosphere. That's information relating to that material right there. They want to know how many grams of copper do I make. All right. Because I have enough information to figure out moles for just one reactant, it's an ideal stoich question. If they had given me information to figure out moles for 2 reactants, then it would be a limiting reactant type of a stoich question where I would have to take the time to figure out who's limiting me and do all the calculations after figuring that out. All right, well, what do I do with this information? What does this information allow me to solve for? Moles. Using which equation? The ideal gas law, PV equals nRT. All right. When I put these numbers in, it's going to tell me moles of hydrogen. So if you look at the paper, there's a little subscripted H2 underneath the N. These are moles specifically for the hydrogen. All right, so I basically isolated the equation for N, so that's PV divided by RT, and then I went ahead and substituted the pressure, the volume, R, and the temperature converted to Kelvin. All right, so that tells me that that is 0.250 moles of hydrogen. Once I know the moles of hydrogen, right, now it's just a stoich question. I can just set up a fence post to figure out how many grams of carbon that is. All right, so you take the 0.25 moles of hydrogen, you multiply it by the mole ratio. According to the balanced chemical equation, you need 1 mole of hydrogen for every 1 mole of copper. They didn't want the answer in moles, they wanted it in grams, so in a final step I multiplied by the formula weight, the molar mass. and I calculated that's 15.9 grams of copper. Okay? All right, so let's practice, and as soon as we're done with this question, I'm done for the day. All right? Okay. It says solid iron 3 hydroxide decomposes to produce iron 3 oxide and water vapor. If 0.75 liters of water vapor are produced at 0.5 atmospheres and 20 degrees Celsius, how many grams of iron 3 hydroxide were used? How many grams of iron 3 oxide were produced? All right, so first things first, what do I need is stoich. What do I need? Balanced chemical equation. All right, so what is the formula for iron 3 hydroxide? Well, think about it. What are the two ions that are in here? It's iron 3 plus and hydroxide. When I cross those formulas together, what's that compound? FeOH3. It decomposes. So what symbol do I write down next? An arrow. I produce iron 3 oxide. All right, so the cation in that substance is Fe3 plus. The anion in that substance is O2 minus. Cross them. What's that formula? Fe2O3. And water vapor. What's the formula for water? H2O. All right, take a moment. Let's check and see if it's balanced. Okay, already I can tell that the ions are out of whack. I'm going to put a 2 over on the far left to make sure that they're equal. How many hydrogens are there on the left-hand side? 6. How do I get 6 on the right-hand side? Put a 3 in front. All right, now how many oxygens are there on the left-hand side? 6. Do I have 6 oxygens on the right-hand side? Yes, I'm done. Okay? All right, now let's take a look at the information that they tell me in the problem. They tell me that I have 0.75 liters of water. The pressure that that water produces is 0.5 atmospheres. And by the way, that's the only substance in that equation that produces the pressure. Because that's the only substance in that equation that's a gas. Do solids produce pressure? They're not bouncing off the walls of the container. They're sitting at the bottom. All right? And the temperature of that vapor is 20 degrees Celsius. So for part A, they want to know how many grams of this stuff, this reactant, did you need to make that? All right, so what do we do? I'm going to use the ideal gas law, PV equals nRT, to figure out moles of water. All right? Moles of water, if I rearrange that equation, how do you get N alone? What is it? Is it PV divided by RT? I'm going to substitute my pressure. The unit that they gave it to me in is good. I'm going to substitute in my volume. The unit that they gave me that in is good. I'm going to substitute in the gas constant, and I'm going to take that temperature and convert it to Kelvin before I plug it into that equation. So let's see how many moles of water that is. 0.5 times 0.75 divided by 0.0821 divided by 293. Okay. Okay, so I get 0.01558 moles. It's got a lot more decimal places. I'm not going to round it, because if I round it, it's going to screw me up. I'm going to leave the number in the calculator, because I have to continue the calculation, right? Now that I know moles of water, right, what do I do from that point? For every 3 moles of water, I need 2 moles of iron 3 hydroxide, and then 1 mole of iron 3 hydroxide weighs a boatload. How much does it weigh? It's 55.85 plus 3 times 16 plus 1. Okay? So I'm gonna basically calculate this out of the ideal gas law. Leave this number in my memory. You see it's a very long number here. And then I'm going to leave it in memory, and I'm not going to round until I get to the very end after this fence post is said and done with. So I'm going to multiply by 2, divide it by 3, and then multiply by that molar mass, which is something yucky. Oh, and look, I get 1.11 grams of FeOH3, but you may notice that's too many sig figs, right? How many sig figs am I allowed to report? Look at what they gave you. They gave me the volume to 2 sig figs, the pressure to 1, and then this ends up being 2 sig figs after you add 273. So how many am I allowed to report? 1. So the answer is just 1 gram. Okay? All right, how do you do B? Do we have to do this again? No, we did it already. You can go ahead and start the next one just with the fence post, 0.1558 mole of water. Using the mole ratio between water and iron 3 oxide. So there's 3 moles of water for every 1 mole of iron 3 oxide, and then converting back to grams. That's 2 times 55.85 plus 3 times 16. I get 0.8 grams Fe2O3. Did you get that? Yeah? All right, are we good? That's what your homework's all about. Do you think you can do it? Again, this last thing, it was an ideal stoic question. Could I have done it in the context of a limiting reactant problem? Sure, I could have. In a week or so, I'll pull out FRQs. Let's see what the College Board would be willing to do to you, if they'd be willing to go to that extreme. Okay? Yeah, go ahead. Just go. Why won't it stop? Go. Just go. Why won't it stop recording?